In other words, if this goes well, you'll get food. If not, I will stand up here and eat all the food.
That's awkward conditioning, not the right person.
Okay, so here we go. Here we go. And here we go. Okay, we're not going yet. Hold on. There we go. Okay. So we're talking about area. So you're asking yourself, what does he mean about area? Well, I'll explain that to you. That's what's called the concept. We'll talk about calculating area. Is it safe to assume you could all find the area of a rectangle? Beautiful. Then this, no. That was me mocking you, by the way. If you can find the area of a rectangle, then this lesson should be pretty easy. We're going to relate area of a rectangle to a limit, and then as you continue to work on antiderivatives, you should try to draw that integration symbol and not make it look silly. Okay? Any problems? So you'll recall that when we talked about derivatives, there were three main, I don't want to use the word definitions, but three main ideas about derivatives. What were they? What does a derivative represent, I guess is the question. Good. And then the second thing was? Instantaneous velocity is one of them. Excellent. Slope of the tangent line and? Yeah, rate of change. Good. Integrals have a similar idea. Only one though. And it is the area under a curve. That's it. So its physical representation is the area under a curve. So if you graph a function, it would be the area from the curve down to the x-axis. Which means we should get a numerical answer. Because area is a number, right? The problem is we haven't gotten numbers yet. We've gotten functions. When we take antiderivatives, we get another function. So somewhere along the line, we have to be able to get the stuff we've already done with antiderivatives and integrals to equal a number. But before we do that, we're going to talk about this idea of the function being an area under the curve. So I have a couple pretty pictures for you. Come on, cooperate. There we go. Okay. So what I've got in this picture is I've got a function which is represented by that red line or that red curve. And I took the area under that function and broke it into rectangles. Because rectangles are easy to find the area of. What's wrong with that? Ton of spaces. Right, so you'll see that there's some stuff over here that's above the curve. I've got some openings under the curve. So that's not going to give me an exact answer. I want an exact answer. I want to know, accurate to an infinite number of decimal places, what the area under the curve is. So eventually we'll get to that point, but we're going to start by approximating using rectangles. So based on this model, how could I get my answer more accurate? Could use trapezoids, but I'm only using rectangles now. That comes later, by the way. I'm sorry? Was that a wow? Yes. Oh, okay.
Smaller sections.
Smaller rectangles, correct. Okay, which I just happen to be able to do with this snazzy program. Yeah, that's pretty cool. So if I increase the number of rectangles, then the amount of wasted space decreases. Two things that we're going to use, I think this is the right word, synonymously, we'll try it, is increasing the number of rectangles or decreasing the width of the rectangles. Do you understand that they would be the same thing? Okay, by the way, the width of those rectangles we call delta x. I don't know if you can read it, but it said there's a little delta x down there. So that's how big those are. Okay, so let's go back to the big fat rectangles and talk about, ooh, that would be really bad right there. That would be horrible. Yeah, that's, I didn't pay attention at all. Okay, so let's go to something reasonable like this. So I've got delta x, and I can figure out the height of each of those rectangles. So let's take the farthest right rectangle. You'll see that it's just touching in that one little corner there. It's touching in the upper left-hand corner. That's called a left-hand rectangle, because it's touching on the left-hand side. You with me? All of those, in fact, are left-hand rectangles, because the point that it contacts the function is on the left-hand side. Left, 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 left. Some of those left-hand rectangles are above the curve. That's called circumscribed. Don't know why. The ones below the curve are called inscribed. You'll also hear me use the terms upper limits and lower limits. So if it's above the curve, it would be an upper limit. If it's below the curve, it would be a lower limit. And we can go and count. So how would I get an answer to the problem? What would I need to know? Let me rephrase my question. How do you find the area of those rectangles? Say again? Base times height, right. Base times height 6 times. So if we look at that right-hand rectangle, and for discussion purposes, you may have to look at the screen by you. Let's say that that left-hand edge is at 8.2. How would I know the height of that rectangle? No.
The y-axis?
Be more specific.
The value on the y-axis?
Value on the y-axis, correct. Okay, so the height of this rectangle starting from that point is the same as that value. What if I knew the function but didn't have the picture?
You plug it in. Plug in the x value and then you get the y value.
Perfect. Okay. So the height of this rectangle is f of x. The width is delta x. And we choose that delta x. Now, we're not going to choose something weird like 0.6. We're going to choose something nice like a half, 1, et cetera, to make our calculations nice and easy. Okay, so is it safe to assume that you could do that? And I have some examples where we'll actually plug in numbers. I just want to make sure you understand the concepts first. Okay, now what if we switch it to the other side? Boink, they change colors. First of all, that doesn't always happen. But notice now these are right-hand rectangles. The right-hand edge of the rectangle is what's contacting the function. Some of the rectangles are above the curve, some of the rectangles are below the curve. And so you'll get different values. You'll get different values, and the problems would say something like, approximate the area under the curve by using right-hand rectangles, using left-hand rectangles. Okay, it just depends on which side you go up or down. You'll also get questions like, is your answer an over-approximation or an overestimate, or is it an underestimate? Okay, in this case, if I calculate the area of those 6 blue rectangles, would you think that that answer would be bigger than the actual answer or smaller than the actual answer? Why?
There's more like above it.
Say that, one of you say that again.
There's more.
Or both of you point at each other and then nobody say anything.
There's more above the function than there is below the function.
Are we in agreement there? Okay, good. The area above the curve is bigger than the area under the curve, and therefore we would have an overestimate. Notice that this function, is it increasing or decreasing? What did you say?
I said yes.
Yes, correct. It's both. It's decreasing and increasing. Okay. So therefore, let's look at the increasing part. Right-hand rectangles with an increasing function. Good news, above.
Oh, good news.
Right. Decreasing function, right-hand rectangle, below the curve. If we go back to the left-hand rectangles, or just move that out of the way, it switches. And so you're going to have to get comfortable with the idea of what shape is my curve in determining whether the function whether the values are above or below the function. Any questions before we go back to the slideshow? And so here's like a whole parabola, you can play with all that fun stuff and.
You just repeat like the decreasing, increasing, like lefty, righty stuff. So if it's a right-handed triangle, if you do right-handed triangle or a rectangle, then it's increasing.
Hold on, let's go back to the slideshow and we'll draw some pictures. Okay, what do you want to do first? Increasing?
Sure.
If I've got an increasing function, by the way, that's increasing concave down. We'll have to talk later whether or not the concavity affects the answer. And I do left-hand rectangles. Okay, so I'm going to go from here, 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 extend this, here, and here. So I'm going to do 1, 2, 3, 4 subintervals. Remember, this is delta x. Now, to make a left-hand rectangle, the way I do these problems is I take my gradients, which is what those are, and I just draw segments up to the curve. Okay? If I'm going to do a left-hand rectangle, then I go up the left-hand side and go across. If I'm going to do a right-hand side, I go up the right-hand side and go across. So you said left-hand first, Paul?
Sure.
Doesn't matter. Go up the left-hand side, come across. Go up the left-hand side till you hit the curve, come across. So there's 1, 2, 3, and 4. Hey, everybody, it's Mr. Beloff.
Hi, everybody.
Wow, that was
I mean, that's pretty,
Somebody's
well,
gonna
that's what
get-
happens when you have 6 days off.
Yeah,
How many people took 7th day? 7th day?
yeah.
6 was enough? You're on the 7th one? Or did you take one off at the beginning?
It's an 8.
Whatever, you know.
You know what it is?
It's an integral. It's a little rectangle.
Underestimate or overestimate?
Middle estimate. Why not? Just go in the middle, baby.
Which one is that?
That's under, baby.
Okay, left hand or right hand?
Well, you did it with your left hand, so I'm going to call it left hand.
You're right.
No, he's correct.
That's not why.
See what I did with that?
Yeah.
You stop by for a visit?
Yeah, I was swinging by because I just had finally gotten one more consent form in. Dual credit. I love it.
Love it. Awesome.
Do it! Where's class?
Religions and college comp.
Not the one. See, because I haven't come.
Couch com?
Couch comp. Yeah, you learn how to like sit on a couch.
That would be awesome.
That's religion.
Nice and nice.
A lot of
You
colleges
get, like-
are like that though.
Different couches to try out, some with built-in recliners. Some are fancy, like 17th century couches.
Kind of feels that way.
Yeah.
You get a lot of like snowfall going on, huh? As it melts, it keeps falling.
Every once in a while, it looks like a body's falling past the window. This big, a big chunk comes off there. It's like, I hope that was snow.
All right, good luck, Mr. Reedy.
Thank you very much.
Bye, class.
All right, where were we?
The triangle.
All right, so increasing concave down. Increasing concave down. Left hand rectangles. And we get an underestimate. Because they're all below. So let's do the same thing, but change it to concave up and see if that matters. Increasing concave up. Does the concavity matter? No, it doesn't appear to be. Increasing concave up, left hand, both underestimates. So what do you think is going to happen if we switch to right hand?
It's going to be an overestimate.
Right, so now we can change a number of things. We can change to right hand, stay with increasing concave down, increasing concave up with right hand and see what happens there. And then we can change the function, go to decreasing concave up, concave down and see what happens. I'm not going to do them all because you get an idea and you can all draw pictures on your own. Get rid of this. And let's move on. All right, so you got the basic idea, right? Yes or no? Good, so all you gotta do is find areas of rectangles. Literally, that's all, there's no trick here. I'm not gonna all of a sudden pop something on you and say, oh wait, but you got it. No, this is it. Find the area of the rectangles. Most of the difficulty is going to be in learning the terminology and understanding what the problem is asking you. Okay, so we'll work through some examples. We saw this already. Yeah, blah, blah, blah. We did that. Okay, great. Delta x. Oh, hey, how do you find delta x? Now, normally, well, not normally, but sometimes it'll say, break this area into 5 rectangles with a width of blah, blah, blah. But that's too easy. Most of the time, what they'll say is, we have a region from 0 to 10, and I'd like to approximate the area under the curve using 5 regions. 0 to 10 into 5 units. 10 minus 0 is 10 divided by 5. Each one's 2 units wide. Most of the time you'll get nice intervals. 1, a half, 2. Sometimes they'll be a little saucy. 0 to 7. Or it might even do something like 2 to 7 with 6 intervals. Yeah, that's nasty. This is what we talked about already. The area of under that curve would be 2, which is the width of each one, delta x times the height of each rectangle. And as we mentioned, the height of those rectangles are determined by the value of the function. F of 0, f of 2, f of 4, f of 6, f of 8. Why not f of 10? Because f of 10 is not touching the function. Okay, so this first rectangle, for instance, the height of that rectangle is this height, and that height is finding what f of 0 is. The height of this second rectangle is the height at 2. That's the f of 2. F of 4, f of 6, f of 8. Okay, you're not going to use values that aren't touching the function. Make sense? Beautiful. Right-hand rectangles, same thing, just on the other side. Now notice in right hand in this case, I'm including the 10 because it's hitting at 10. It hits at 2, 4, 6, 8, and 10. As you start to get into these problems, the one thing that I would highly recommend is drawing a sketch, because this will allow you to visualize what you're trying to do instead of trying just to muscle your way through it. Draw a quick sketch. Doesn't have to be 100% accurate. Draw some vertical segments and then figure out what your rectangles look like. Okay? In this case, for instance. They've got a function. Sometimes you'll know the function, sometimes you won't, depending on what information they give you. Using left and right hand endpoints, approximate the area of the region below 1/2 x squared plus 2 using 3 rectangles in an interval from 1 to 4. Okay, so KISS method first, kept it simple. What's delta x? 1. Any problems with that? 4 minus 1 divided by 3. Delta x is equal to 4 minus 1 divided by 3, which is 1. We'll do left hand first. So again, being a visual learner, I'm going to go to 1, 2, and 3, and 4. And starting at 1, draw in my vertical lines. And since I'm doing a left-hand rectangle, I'm going to go up the left-hand side of the first rectangle, come across. Left-hand side of the first rectangle, or second, and the third. So here are my rectangles. And again, we're going to use a very simple approach. I have 3 rectangles now. All I need to do is find the area of each of those 3 rectangles. Did I lose anybody there? Are we good to go? Does this seem inherently simple? Yes? Does it seem so simple like you think there's going to be a twist?
Yes.
There isn't. Okay, I can't say it enough. It's just find the area of those 3 rectangles. Excuse me. Okay, so Roman numeral I. That's a little hard to see. What's the area of I? Don't be bashful. How wide is it?
1.
1. How high is it?
F of 1.
We're going to start simple here. We'll do the calculations in a second. Is everybody good with that idea? Which side of the rectangle is touching the function? The left-hand side, which is at 1, so therefore the height is going to be f of 1. Tim, question?
Oh, no, I just had to answer.
To this?
Yeah.
Okay, we'll come back. Let me list all of them. What's the area of rectangle 2? How wide is it? 1. How tall is it? F of 2. And then area 3, 1 times, hopefully you see that it's f of 3. And notice we're not using f of 4 here. All right, Tim, over to you. What's f of 1?
Like the area or just the
Just f of 1.
f of 1 is 2.5.
Okay.
And then you multiply it by 1, and it's, so the area is 2.5.
Okay, what's f of 2? Where did, by the way, does everybody see where the 2.5 came from, or the 2.5? Plug 1 into the function. Good to go. What's f of 2?
4,
4 times 1 is 4. And f of 3?
6.5.
9.5. It's 13 halves? 6.5, same thing. Yeah, 6.5. 10, 9, 13. Done. I lose anybody?
Oh, right.
Good. 3 rectangles, 3 areas, add them up, done. How's it going to change if we do right hand? Okay, hold on a second. Underestimate or overestimate? Under. Is that obvious from the picture? Yes. And I think that if I grab any schlub out of the hallway and bring them in here and show them that picture, they'd be able to tell me it's an underestimate. Doesn't involve calculus knowledge. Another selling point as to why you should draw a sketch. Let's switch to green, because it's the holiday season. I already have my vertical lines. Now I just have to go up the right-hand side. So I'm not going to go up the right-hand side of 1, because that would put over here. So I'm going to go up at 2, go up, hit the function, come across. Up 3, hit the function, come across. And then go up 4, hit the function, come across. Before we even start the calculation, overestimate or underestimate? Over. Okay, good. And we already did most of the grunt work. Notice the area of those 3 rectangles. This is a visual, so look up here. This rectangle in green is the same as the second rectangle in red. The second rectangle in green is the same as the third rectangle in red. So really all we need to do is find the area of that rectangle, which we'll call the area of IV. 1 times f of 4. Which is 16.8 to 10. So then the green would be 4 plus 6.5 plus 10. 20.5.
Then you just take the average of the 2 and find them?
No, that would be way too easy.
Oh.
Yeah. Getting the exact answer is going to be quite a bit more complicated.
So for now, we just say between 13 and 20.5.
Yes. If somebody puts a gun to your head and says, "What's the actual answer?" you would say, you know, and it would be it's got to be somewhere between 13 and 20.5. How we find that actual number is another lesson.
Take a shot and say like 17.
Don't say that when somebody's got a gun to your head. Bad word
17.
choice. Okay. We good?
17.
There is a third method, which we're not going to do a lot with, but I'll just mention. There's another thing called a midpoint rectangle. You're all smart fellers. What would be a midpoint rectangle?
It's not left or right. It's
Right. It's in the middle. So you would go up at 1.5, hit the function, go left and right. Go up at 2.5, hit the function, go left and right. Go up at 3.5, hit the function, go left and right. So that's a third option. We don't deal a lot with that because we don't need it. Any problems here? Again, easy concept? Yes. Okay, so eventually this isn't going to work anymore. I'm not going to want approximate answers. I'm going to want the exact area under the curve. And we talked about how to do that. We need to increase the number of rectangles. How many rectangles? Infinitely many. So we either want the number of rectangles to go to infinity or delta x to go to 0. That sounds mysteriously like a limit. Not now, not now. Again, I'm not, I didn't lie to you. It doesn't get any harder than this. This is all we're doing. Oh, I chose yellow. Okay, so let's check our answers. Did that. Oh, 13, that's what we had, right?
Yes.
Okay, good. And then right hand, we had one foot, there was red, and then 1, and then 20.5.
Yes.
We're good? Excellent. Upper and lower sums. Ooh. Ooh. A lot of fancy calculus speak on this page, but we've already talked about this. And we just finished this conversation. Notice I've got lowercase s of n and uppercase s of n. Lowercase s of n is the underestimate. Uppercase s of n is the upper estimate. And we already discussed that phrase in the middle. Little s of n is less than the actual area, which is less than the capital S of n. And just to refresh, or to say again the terminology, if your rectangles are below the curve, it's called inscribed. If your rectangles are above the curve, it's called circumscribed. Now, there's one other thing that gets a little bit weird. If you all right? Okay. Look at the left-hand picture, or not, I don't want to use it. Look at this picture on the left. What do you notice about those rectangles?
None of them are over.
Some of those.
Good, none of them are over. Those are all inscribed rectangles. What else do you notice?
Some are left and some of them are right.
Good, some of them are left and some of them are right.
And then one of them.
Okay, does everybody see that? So, depending on the problem, it might say using left-hand rectangles. It might also say using right-hand rectangles. Those are just like what we've already done. However, the problem might also say using inscribed rectangles. If you use inscribed rectangles, you just have to make sure that each of those rectangles is below the curve. So when you're going to decide then, do you want to go up the left-hand side or the right-hand side? It's whichever side is going to hit the function first and stay below. If you're doing circumscribed, then it's whichever side is going to go up above the curve. So we can throw all that in the mix, and makes for a little bit more complicated scenario depending on what the problem is asking you for. And sometimes it won't matter. If the function is always increasing or always decreasing, they would be the same thing. Okay, so again, inscribed, circumscribed, we got that. So we'll do one of these
It's the same, but
to show you the difference. Well, actually, there isn't any difference here. Inscribed versus circumscribed. With this function that we've already worked with, which one would be inscribed, left hand or right hand? Left. Which one would be circumscribed? Right. Now, why doesn't this change at all? Because the function is continuously increasing. If the function turns over and starts to decrease, then we have different rectangles.
Like we extended it over there.
Correct. If we came over here to -1, then it flips over there and you've got to decide, are you going to use the left hand and the right hand? But again, the sketch will help you solve that. And it's just a matter of drawing a picture and finding the area of rectangles. We good? All right, again, don't overcomplicate this. It will get more complicated, but not yet. Draw some sketches, calculate some rectangles.